Hello guys, this is just a very short video about some remarks that I want to say about this lesson 5.3, derivatives of the most common functions. I already wrote the workbook 5.3 and I told you that I'm going to keep doing this for every single lesson. I'm going to give you a workbook with some of the theory that entails such lesson and with the exercise that you have to perform. Okay, so all the theory in there is pretty understandable, and there isn't much to say about this topic. I'm sorry about this lesson, other than I'm gonna give you a table of the main functions that we're gonna look throughout the course, and you know all of this. Okay, you have your constant function, your power function, your polynomial function, your um, trigonometric functions, exponential functions, logarithmic functions, and so on. All the basic functions that you have seen so far. And I'm going to give you its corresponding derivative f prime of x, the corresponding formula for its derivative. The only things I want to tell you is that we're not going to prove these formulas, most of them. I'm only going to prove the one about the constant function, which is this, f of x equals a. If we have this type of function, f of x equals some constant, then the derivative f prime of x will always be 0, no matter what the constant is. And I'm going to perform this one in a minute. And we have already proven that if f of x equals x to the n, when n is a natural number, or in other words, if n is a positive integer, then we know that the derivative f prime of x is going to be equal to n times x to the n minus 1. And we have already proven completely this result. Okay, I took you from scratch to this result. Whether you forgot about it or actually remember it doesn't make any difference. I showed you how it's done, and I showed you how by applying the definition of the derivative we can get to this formula, which makes our lives very simple in regards to calculating derivatives. So these are the only ones that I'm going to show you in close detail, because for most of them the demonstrations are not quite simple. They are very time consuming. I may confuse you even more than what you could be, so I don't think it's a very good idea in high school to go over the demonstrations of the derivatives of each of these functions. Those that are interested among you could look them up on your own. Okay, I think it's a good exercise. Those of you who are more mathematically oriented, or want to go into engineering or sciences or economics, that sort of thing, look them up on your own. And if you have questions about that research, you can ask me, okay? And I may be helping you. I could help you out with that. I'm going to be very happy to do so, but not as a general thing. I'm not going to do that for everyone. Okay. Another thing that I want you to notice in this table that you're going to see in the workbook is that when I write this particular formula, okay, you're going to see the next. F of x equals x to the n, but now I'm allowing n to be any real number. This n, this exponent, can now be any real number. So basically it has no constraints, no restrictions. And the formula will be the same. F prime of x equals n times x raised to the n minus 1. So the new formula that is going to appear in the table is a more general formula for the derivative of this type of function when n is any number, any real number, because before we only proved it for natural numbers. Okay, so that's all about this table. You have to memorize the derivatives, and that's your whole duty. Okay, just memorize them. You don't have to understand the demonstrations because they are actually complicated. Okay, and the rest of the workbook, I think that when you read it, you're gonna understand that it's actually pretty simple to get all the exercises done. Of course, you're gonna have some trouble because you're not used to compute derivatives, but the general idea is very simple, and you just need practice. That's it. Okay, so let me demonstrate that when f of x equals a constant, your constant function, then the derivative of f, which is known as f prime of x, is going to be always equal to 0 all the time, no matter what this number is. If you give me f of x equals 5, if you give me f of x equals the square root of 2, if you give me f of x equals e to the 2, whatever, all of these things are constants, right? We know the values of these things. Then for each of these things, the derivative will always be 0. Always. For whatever constant. How do we prove that? It's very simple. In the only way we can actually prove this thing, which is following the definition of the derivative. Following the definition. What is my definition? My definition is this. If I have this function, then the derivative of f, which is known as f prime of x, well, it's read in this way, f prime of x, it's going to be equal to the limit as h goes to 0 or as h approaches 0 of my quotient f of x plus h minus f of x over h. That's it. That's the definition. So let's continue working with it. That means that f prime of x is going to be equal to the limit as h goes to 0 of f of x plus h. But you have to understand this about the constant function. The constant function basically, the main characteristic of this function is that when you evaluate it in any number, if I consider this f of x, then f evaluated in whatever number will always be a. F of 2 is going to be a. F of minus 1 will be a. F of 1/2 is always a. Okay, that's what it means. That's why it's called a constant function. And it's visually very understandable because this function, when you graph it, is going to look like a horizontal line that crosses the y-axis at a. So this is f of x, this is x. So for whatever value of x, for this value of x, for this value, whatever number that in which you evaluate this function, what's going to be the resulting output for the function? It's always going to be a, you see? It's always a for whatever number of x. So once we understand that, let's go back. Let's go back here. So what's going to be the evaluation of f in this number, which is known as x plus h? Well, it's going to be a because of the reason I told you here. It doesn't matter what number you evaluate in. F of anything will always be a. F of anything is always going to be a, always. So all of this is a minus f evaluated in x. That's a because of this. Over h, we continue, f prime of x equals limit as h goes to 0, a minus a, that's 0 over h. We continue over here. Therefore, f prime of x is equal to the limit as h approaches 0. 0 over h is always 0. Okay? When you divide 0 over any number that is not 0, and remember that h is not 0, it only approaches 0, then you have that 0 over h is 0. And basically, the limit as h goes to 0 of 0 is going to be 0. So f prime of x is equal to 0. Because this variable that you have in here, h, doesn't even appear in your function. You see? It's not even here. So it's just automatically 0. Automatically. And therefore, we have proven that the derivative of the constant function is always 0, regardless of what constant we're talking about. Okay, so that's it, guys. You have another proof, constant function, the derivative of a constant function, and now let's work on the workbook. Please read everything I wrote, memorize the formulas for the derivatives, and get through all the exercises. So thank you.